with functions, we've graphed functions. We know that the graph of a function is really just a representation, like a graphical representation of like all the xy pairs, right, that fit the function. I could plug in an x and I get out a y, and boom, that's a point on the graph. I could plug in an x, I get out a y, boom, that's a point on the graph. If it is a function and not just an equation, it'll pass what we call the vertical line test, right? Every input can have only one output. But as it turns out, that concept of like the input and output doesn't quite suffice for some of the questions that we want to answer in mathematics. So what we do is we introduce, or some people did, several hundred years ago, the concept of a limit. So here's what the conceptually what a limit is. And then I'll write down sort of a more rigorous definition that is true, but for the most part, like what this sort of conceptual notion of what a limit is going to be good for us. So here's a function. It's a nice smooth curve. We would call it continuous. We say that the limit as x approaches c is L, because as I let my x coordinates kind of creep up on c from either direction along the curve, right? My y coordinates just get closer and closer to that value L. And at this point, you might be thinking, how is that different than just saying f of c is equal to L? And for a nice continuous curve, there is no difference. We're going to look at some more interesting examples in a little bit. We say that like as x gets close to c, if we let x get arbitrarily close to c, then f of x values, those y coordinates, get arbitrarily close to L. That is conceptually what a limit is. We have a more rigorous definition, which is referred to as the epsilon delta definition. And I'll write that down. And it goes like this. The limit as x approaches c of f of x equals L if for every epsilon greater than 0 there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus delta, the absolute value of x minus c is less than delta. So here's the idea. It says for every epsilon greater than 0. The whole idea is that epsilon is tiny. It just has to be positive, but like make it tiny. You're saying, here's how close I want you to get. So you kind of make a little band around L. Be like, get me within that ballpark. It's like a challenge. I'm going to make it super, super close. And no matter how small you choose to make epsilon, no matter how close you want me to get to epsilon, or me to get to L, right? No matter how small epsilon is. Like, maybe here's my epsilon band. That I could kind of trace this over and find the window around these values. Like how close? Like you give me an epsilon, so I draw this little epsilon band around L, and I can kind of trace that over and say, there's my delta. I just need to be that close to my input, right? And so if I can do that no matter how small you make epsilon, that means that that is what the limit is. It doesn't require the function to be defined as c. The limit can exist even if the function doesn't exist. The limit can exist even if f of c does exist but is not equal to L. And we're going to see some of that on the next page. So here's a graph of a function. We don't have an equation, but it's a graph of a function. And look, this function does something weird at x equals 3, and it's situations like these that make us want to define a limit. So to kind of describe the weirdness, the reason that it's weird is because f of 3 exists, right? What is f of 3? Can we use What's it say that?
2.
2, right? So the little hole here means that, like, here I am on the function, these are all the outputs, but I get to that hole, and that means, oh no, f of 3 is not here. That's what that indicates. And they've filled in the hole somewhere else. They don't always fill in the hole. Like, it could just be that f of 3 doesn't exist, but they've chosen to fill it in, right? And then as soon as I'm not at 3 again, I'm back on this nice smooth curve. That is a function, right? Every x has only one y, and 3 is even in the domain, right? Doesn't matter what x is, I'm going to be able to plug it in, get out a y. It's a function. So f of 3 is equal to 2. But what is the limit as x approaches 3 of f of x? Like, if I kind of trace along the graph and I let the x values kind of creep up on 3 from either direction, what do my y values approach? 1. This weirdness in the graph is an example where a function is not continuous. So this function is not continuous at x equals 3. It is continuous everywhere else. Nice smooth curve, right? We had an intuitive sense of what it means to be continuous is that I could sketch it without lifting my pencil. So here we have a spot where I kind of have to jump over or jump up, fill in the dot, and then come back down on the curve. Continuous everywhere else, but just not at 3. So something interesting is happening there. So the whole idea of continuity is central to calculus. A lot of all of our results that we'll use in calculus is assume f of x is continuous, provided that f of x is a continuous function. Then we get to do all these things. And here's what it means to be continuous at a point, right? So when we talk about continuity of a function, we really mean continuous at a particular point. And in order for a function to be continuous at a point, the function has to exist there. Like, I have to be able to plug it in and get an output. The limit also has to exist. And the limit has to be equal to the function value. So this is not continuous up here because it failed the third criteria, right? The first two criteria are fine. The function exists, it's 2. The limit exists, it's 1. But they're not equal, so that makes it not continuous there. When we talk about the limit existing, I said this a couple of times, but I'm going to really emphasize it now. In order for the limit to exist, it has to approach the same thing from either direction. All right? So, like, another way, like something, like one way, okay. Let me start off. We know what something could look like for the third criteria to fail. The way something might, like, if the first criteria fails, like f of c exists, like if that's not true, would be if up here they just didn't fill in the hole, right? They didn't assign f of 3 any value, and it was just a hole and nothing else, so it wouldn't be continuous there still because the function doesn't exist. The way that the second criteria can fail, where the limit itself doesn't exist, might be something like, I'll just sketch this off to the side. The limit x approaches c of f of x does not exist. This isn't the only way that it could happen, but like maybe I have my curve that does something like this. The limit doesn't exist because if I approach c from the left, my y-coordinates approach 2, but if I approach c from the right, my y-coordinates approach 1. So the limit itself doesn't exist. You can define a left-handed limit and a right-handed limit. So we would say the way we might write that here is that the limit as x approaches c from the left. So we put a little superscript minus sign. That means from below. That's equal to 2. And the limit as x approaches c from above, from the right, is equal to 1. But the limit doesn't exist. For just the plain old limit to exist, it has to be the same from either side. So there's another function that's not continuous.
So wouldn't, as x approaches c from the right, wouldn't the limit also be 2 though, because the circle is empty?
Nope. As you approach, if you approach x, how do I get close to 2? As I approach it from the left. Right? So give me any epsilon, tiny as you want, and I can tell you how close to get, I could find a delta within C to get. Since this is a right-handed limit, we're approaching it from above, I'm only considering like a kind of an epsilon band on one side or a delta band on one side. How's that? Nice? Yeah, okay. Let's keep going. Let's talk about continuity some more. And we'll do it just by examining some graphs. So we're going to look for weird stuff, or look for places where it's not continuous. Any weirdness, or where do we think it is continuous? Where do we think it's not continuous? Let's start with part B. Where do we think that is not continuous?
X equals 1.
Yeah, right, so this is x equals 1. So this is not continuous at x equals 1. Why?
Because the line jumps higher now.
Right, there's a jump, right? So like intuitively I can't sketch it without my pencil, without lifting my pencil from the page. Which of these criteria is violated?
Number 2.
Yeah, the limit doesn't exist because it's not the same from either direction, right? So the limit as x approaches 1 does not exist. Do you have any funny business like that happening in part A? No. So the thing that might be interesting in part A is that the domain is obviously restricted, right? The domain seems to start at x equals 1, but other than that, it seems to be continuous. No funny business happening there. So we would say that this is continuous on its domain. Which is x greater than or equal to 1. In part B, we identified that it's not continuous at x equals 1. Everywhere else, though, it seems to be pretty smooth sailing, so we might just add a note that it's continuous everywhere else. What do you think about part C?
It's not. Because
Not.
it's not a function. Correct.
Oh, it's a function.
You get this. I thought you said if the hole's not filled in.
Well, that just means so it is a function. But the function is not defined there
Okay.
at that one value.
Oh,
So we have a continuity problem at -2, right? So this is not continuous at x equals -2. We would just say that the domain of this function is all real numbers except -2, right? Just -2 is not the domain, which is another way of saying that f of -2 does not exist. Seems to be continuous everywhere else. So notice how we're kind of going about these continuity questions. Like if we're wondering where's a function continuous, it makes sense to kind of just ask it the other way around. Where's it not continuous? First, let's find the problems, let's find the issues, and then say, okay, everywhere except for these places, it's continuous. So here's kind of what it looks like with a graph. We're trying to identify the kind of funny business that's going on by looking for holes or jumps or something. What kind of funny business is going on in part D? Or where do we suspect we might find a problem?
2.
At 2, and why is that?
Because you'd have the zeros to denominator.
Yeah, we can't divide by 0. So this is not continuous at x equals 2 because f of 2 doesn't exist, right? We can't plug it in. We can't divide by 0. As it turns out, this whole like not being able to divide by 0 is something that has inspired and motivated why we need limits in the first place. And it's going to be something like that allows us to do kind of cool things with analyzing the graph of a function. Continuous everywhere else, right? If I plug in anything except for 2, I could still divide by 0. And if you graphed it, you would see we'd have mostly a smooth curve except for some weird stuff at 2. If you graph it, it looks something like this. You have a little asymptote, and then this does something like this. And this. Like if you think about it, as I get really close to x equals 2, this becomes really close to 0. So when you divide a constant by tiny, tiny numbers, like if I take 1 and divide it by a tenth, you get 10. If I take 1 and divide it by 1/1,000,000th, you get 1,000,000. If I take 1 and divide it by 1 over 20 billion, I get 20 billion. So like the closer this becomes to 0, the bigger these numbers are. And then whether it's shooting upward or downward just depends on whether that denominator is positive or negative. As x gets huge, we're taking 1 and dividing it by huge numbers, so it approaches 0. What about the last one? Any funny business there?
So it's continuous.
Yeah, everywhere, right? This is continuous on all real numbers because there are no jumps, no danger of dividing by 0, and those are really what we're looking for. Those types of jumps might happen, like the way we would detect like this kind of behavior here in part B, we'd be able to detect if we saw it in a function written out as an equation because they would define it as a piecewise function. So this would be like f of x equals, and then they'd have like little brackets, and then they'd have 2 different rules. So it's usually pretty simple. It doesn't mean that it's never continuous because it's a way to define those functions in a way that it still makes it continuous, but like that's how I know where to check for continuity. We also know what this looks like, 3x squared, right? I mean, it's a parabola centered at the origin, so like that's a nice smooth curve. We could graph it. So this talk about continuity is really closely related to limits, and we're going to take some time thinking about how we evaluate limits. And we're going to start by evaluating them numerically, and I should really say, I'm going to do a little strike through. I should really say like estimating. Because, at the end of this process, all we could do is say, I'm pretty sure it's this. Looks like it's going to this, right? And so the exercises in this for limits are split up in 3 groups. This last group is they talk about continuity, and I think all these problems are kind of looking at graphs like that last example, so there's not a lot of calculations to do. And then we have doing them evaluating limits like graphically or numerically, like what is this approaching? And then we have a few where we're evaluating them analytically, which is definitely like the preferred way to evaluate them, and we'll spend some time on that today as well. So we're going to evaluate this limit numerically. The limit as x approaches 3 of x squared minus 9 over x minus 3. To start off, we'll just note that like...
It's x, you're going to divide by 0.
Right. Okay, so x equals 3 is kind of a problem. I can't plug in x equals 3. That's fine, I just want a limit. So I'm going to sneak up on 3 from either direction. I'm going to make a little table. I'm going to sneak up on 3 from below, so like 2.9, 2.99, 2.999. And I know that in order for the limit to exist, it has to exist from both sides, so like 3.1, 3.01, 3.001. I'm going to show you a nice feature of the calculator that might save us a little bit of keystrokes. I'm going to start by entering this function on the calculator. Put in my y equals editor. So on top, I have to just make sure I'm putting everything in parentheses. So the top in its own set of parentheses, divided by the bottom in its set of parentheses. And then I'm going to quit to home screen. And my calculator can just evaluate a function. So if I hit vars, which is next to clear, and then I put it in my y equals editor, so I'm going to arrow over to y bars on top. Select 1 for function.
Wait, I'm sorry, how do you get to that?
So from the home screen, vars, which is next to clear. It's the one that shows up in red there. Below the arrows.
Mm-hmm.
Then y bars, I'm going to use my arrow keys to get to y bars. And I'm going to just hit enter for function because I'm going to select the function. And I put mine into y1, so I'm going to hit enter for y1. And then I just use function notation. So I'm going to open up a set of parentheses, plug in my input 2.9, close my parentheses, and it spits out 5.9. Did you enter the function?
How do you put in the function?
I gotta get
Oh, so yeah, you don't want to do that one here. You want to do here, from your home screen. You gotta quit to home first.
How do you put in the function?
You hit the y equals button.
Okay.
Yep. And you just gotta put the top and the bottom in their own sets of parentheses.
5.9, you said?
Yep.
So you have to keep going back each time to plug in a different number?
Yeah, but also, once I've plugged this in, you can bring up the last thing you typed if you hit second enter. So above the enter key it says entry in either blue or yellow, depending on the model of your calculator, and it'll just repeat what you said, so then I can just go back in and do 2.99 and 2.999. So I've got 5.9, 5.99. Right. And then I can go in and do 3.1. So I get 6.1, 3.01, which gives me 6.01, and 3.001. I get 6.001. And the best I could do at this point is say, well, I'm pretty sure it really looks like the limit as x approaches 3 of x squared minus 9 over x minus 3 looks like it's going to be 6. Right, because those are what my outputs keep getting close to from either side. It's a super unsatisfying way to evaluate a limit, and also like I could find I have a book that has got some good counterexamples. I could find it's possible to have a function where it appears like it's getting really close, but you just don't know. It just does something crazy. You just have to get really close to figure out when it does something nutty. So like it's not only is it unsatisfying, but like it's also like no guarantee that you found the actual limit. So what we prefer to do.
Isn't that a perfect square?
It's a difference of squares.
Couldn't you cross out?
That's a really good suggestion. You said, couldn't we cross it out? So I'm gonna return to that in just a moment. When we evaluate them analytically, the first thing we need to understand is that if your function's defined at C, or wherever you want it to approach, if it's a continuous function, it's defined where you want it to be. just plug it in and find the output. If your function's continuous there, the limit exists and it's equal to the function value, right? Like that's the definition of continuity. So if I know my function's continuous, I'm good. Here's we have x squared plus 2, a nice parabola, totally continuous everywhere, and for sure continuous at -2. So if I want to evaluate this limit as x approaches -2, all I'm going to do is plug in -2, which gives me 6. Right, this is continuous at x equals -2. If your function's continuous there, just plug in the thing. And when we evaluate limits analytically, that's our goal, is to rewrite it in a way that allows us to just plug it in. And I think that's what was Adam, right? That's what Adam was getting at when he said, isn't that a difference of squares up there? So can't we just rewrite it? So if we could do some algebra to rewrite this fraction. We can factor the top as x plus 3, x minus 3. And now all of a sudden, look, we can cancel that x minus 3. And this is equal to the limit as x approaches 3 of x plus 3. And now there's no problem. In this limit, x plus 3 is continuous at 3. No problem letting x be approach 3. So let's do it. So we get 3 plus 3, which, as it turns out, is equal to 6. Some really important things I want us to observe about how we wrote this out. I did some algebra. I rewrote the limit. Notice how I carried the lim all the way through. And that is crucially important because we want to write down things that are true. As it turns out, this limit is not just equal to x plus 3, it's equal to the limit as x approaches 3 of x plus 3. The fraction x squared minus 9 over x minus 3, now back in pre-calc we just said, oh, it's equal to x plus 3 because we could reduce it. That's mostly true, okay? But we are in fact only interested in this fraction at the one place where it's not true, right? These are not completely equivalent. They're equal everywhere except the one place we're interested in. And so that's why it's crucial that we keep the limit through. And it's only when I evaluate the limit, it's only when I say, okay, let me plug in 3, that's when I don't need to write the limit anymore. If we graphed this function, you wouldn't be able to see it on your calculator because your calculator doesn't really indicate holes. But an actual graph of this function would look just like the graph x plus 3. Let me try to... Except right here, there'd be a hole. So they're not exactly the same. These agree almost everywhere, right? And almost everywhere, you'll be pleased to know, is an actually technically defined term in mathematics. But they agree almost everywhere, just not at the one place we happen to care about in this problem. Questions on that one? Yes?
So like for that first example,
Yep.
I mean,
Like up here?
if you wanted to just gut check quickly to see if it was non-continuous, could you just plug in that 3 right off the bat?
Oh, to see if it's non-continuous?
Yeah.
Yeah, I mean, I always check. If I'm evaluating a limit, I just say, can I plug this in?
Okay.
And then here I'd be like, oops, I can't. I'm dividing by 0. So then I know I have some work to do. Yep. Other questions? Okay, let's try another one. All of this, I love calculus so much. I'll tell you one reason is like all that hard work we did in pre-calc, like just hammering the algebra, like becoming algebraically nimble, really pays off in calculus. And, in pre-calc we do a lot of algebra because we're being asked to simplify or we're being asked to solve. And in calculus, we start using those powers of like being algebraically nimble to like manipulate things for our own purposes, right? We're like, I don't want it to look this way. I want it to look some way else, and I've got the algebra skills to make it happen. So there's more than one way we can go about this problem. The first thing we might observe, what do you notice about this? Yeah, I can't plug in 0, right? Perfect. So that means I know I need to do some algebra. The algebra, I've got 2 paths. Both are equally effective, and I make no judgment on which one you prefer. You might notice, the last one we had a difference of squares, right? This, we actually still have a difference of squares. Like, I didn't mean to just pack this with the difference of squares problems, but like, this will factor. I've got this squared minus 4 squared. So I could factor it as a difference of squares. You might look at this and think, oh, I'll FOIL this out first and then try to factor. And that's fine. Like, you'll get the same result. When we have a limit like this, where we want to let x approach some number, and that number makes us divide by 0, our algebraic goal is to do enough algebra to, I want to see a factor of x appear up here. Like, I'm hoping. If a factor of x didn't appear up there, even after all the algebra, and I couldn't take out an x, that means the limit doesn't exist, right? Like the 1 over x minus 2, like that just goes crazy there, right? There is no limit. So we could factor this as a difference of squares. If I do that, I'm going to, first of all, remember to carry my lim all the way through. So I got x on the bottom. What do we have on top? How does that factoring look? So 16 is 4 squared, right?
X plus 2? No. X plus 4.
Isn't it just 4 plus x and then 1 minus x? Yeah.
So we get 4 plus x is the first thing. Plus 4 and minus 4. We can simplify both of these factors. The first one is x plus 8. Oh, it's not over 4. It's over x. Sorry. And the last one is just x, right? Because the 4 minus 4 cancels. What am I going to do now? Cancel out the x's. That's what I'm hoping, right? All this time, I'm like hoping that something's going to happen and I can cancel out that x so I can evaluate. And now it's happening. Beautiful. So this is the limit as x approaches 0 of x plus 8. And what does that give us? 8. How nice. This is how you want to approach these limits, the ones we evaluate analytically, like this, is look, if it's something that makes you divide by 0, you're hoping that you're going to do enough algebra and eventually be able to cancel out that problem factor. If I didn't end up with a factor of x, the limit doesn't exist. It means it would actually blow up. It would approach infinity or negative infinity. There's another type of limit that we can evaluate, and these are limits as x approaches infinity. So the limits as x approaches a number, we're saying, can I zero in on a particular number from either direction and see what my y values are approaching? And limits as x approaches infinity are like, what if I have a graph that looks like this, and as x gets huge, if I kind of look at what's going on, as x just gets bigger and bigger and bigger, does it level off and approach a particular value? And if it does, that's the limit. And if it doesn't, maybe it oscillates or maybe it blows up, then the limit doesn't exist. And we'll start by looking at this particular limit. The limit as x approaches infinity of 1 plus 1 over x. And what I want us to do first is just look at this part. What about 1 over x? Like as x gets huge, what does the fraction 1 over x approach? Say that again? 0, right. So since this approaches 0, we're saying as x gets huge, this piece becomes insignificant. It diminishes. So overall, what is that limit? 1. And if you graph this function, and this is just the limit as x approaches positive infinity, we should mention. If it approaches negative infinity, it'll still approach 1. It'll just do so like from below. But it's a good idea to like kind of think about that. Oh, am I letting x get huge positive or huge negative? And does that make a difference? A lot of times it doesn't make a difference. Sometimes it does. So if I were to graph this, it would look like this. So we have this sort of leveling off behavior.
Would the difference be 1 minus 1 over x?
Well, it would still be 1 plus 1 over x, but if x is negative, we'd be subtracting, right? It's still the function 1 plus 1 over x. But if x is negative, 1 over x would be negative, and that's why it approaches 1 from below on that side. So I wanted to look at this one. This one's kind of simple, right? Like, yeah.
How did you know that 1 over x approached 0? Where did you get that?
So how do we know that 1 over x approaches 0? Basically, you're saying, what about... x approaches infinity. So what we're saying is let x get huge. So if x is 100, it's 1 over 100. And if x is 1,000,000, it's 1/1,000,000th. If I can let x grow without bound, and that's going to shrink that's because the top is a constant. There's nothing special about 1 up here. I could have 1,000,000 over x. I could make that constant as big as I want. That's fine because I'm letting x approach infinity. So it might just take, what's that?
If
If it was like x over 1?
Yeah.
Oh, then it would blow up, right?
So that's
Yeah.
fine.
So what matters, as long as it's a constant on top, as long as it's a constant on top, then then a fraction that looks like that will always be 0. So the reason I wanted to do this one first, it's a simpler example, but it illustrates this fact, right? Some constant over x, if I let x blow up, this fraction will approach 0. And so that gives us an intermediate goal for evaluating limits like this. I want to turn every instance of x that appears in these limits into a fraction that looks like this. And in fact, I'm going to generalize this even more. The limit as x approaches infinity of k over like x to the n is 0. So k over x squared, k over x cubed, k over the square root of x. As long as it's not a negative exponent, because that flips it up to the top, that's always going to be 0, right? Like if x approaches infinity, the square root of x also approaches infinity. It just does it slightly slower. If x approaches infinity, x squared definitely approaches infinity. So these types of limits approach 0. And when we're evaluating these limits as x approaches infinity, we want to turn every instance of x into something that looks like one of those fractions on the last page. And we have I like to think of it as a simple algebraic technique that will allow us to do that. I look at this fraction, I say, what is the highest power of x that appears in this fraction?
2x squared is.
Yeah, so it's just the x squared, right? The highest power of x squared is the highest power that x is being raised to. So what I'm going to do, I'm going to multiply top and bottom by 1 over x squared. I'm allowed to do that, right? Like, I'm allowed to multiply the top and bottom of a fraction by the same thing. I'm not allowed to square the top and bottom of a fraction or take the square root of a top and bottom of a fraction, but I can multiply top and bottom of a fraction by anything I want as long as it's the same. So I'm going to just distribute. So on top, we have x squared times 1 over x squared plus 1 times 1 over x squared. On the bottom, we have 2x squared times 1 over x squared plus 3 times 1 over x squared. I'm going to simplify each of these little products, right? Rules of exponents. X squared times 1 over x squared is 1. 1 times 1 over x squared is 1 over x squared. On the bottom, 2x squared times 1 over x squared is 2. And 3 times 1 over x squared is 3 over x squared. Notice now, every time x appears, it is in the denominator of a fraction with a constant numerator. And that's our intermediate goal, because what do these fractions approach as x gets huge? 0. So that means, now I'm going to drop the limb because I'm actually letting x get huge and seeing what we get. What is the top approach? And the bottom? 2. I want to just observe right now, after having done this example, a really important fact. And that is that infinity is not a number. It's not something you can do arithmetic on or algebraic operations on. If we let x approach infinity right off, the top approaches infinity. The bottom also approaches infinity, and as it turns out, infinity divided by infinity is not 1. In this case, it's a half. Sometimes it's -7. Like, infinity is not a number, and those rules that we use on numbers don't work on it. This is the one rule we get to use when we talk about limits as x approaches infinity. These definitely go to 0, and I can take advantage of that. Questions? Yeah.
So you can kind of just use 1 over x squared kind of whenever, just to get that in like that form.
I identified what I needed to use by asking what's the highest power of x that appears in this fraction. So if it was an x cubed was the highest power of x, I would use 1 over x cubed on the top and the bottom. Yeah. Other questions? Yeah.
Doesn't that also lead to like shenanigans where you have the x cubed on the top and x squared on the bottom?
Can it also what? Lead to shenanigans?
Yeah.
Yeah.
Like,
But that just means so if we I'm gonna just change this real quick. Limit as x approaches infinity. You said what if we had an x cubed on the top? And then I'm just gonna leave the bottom as is. So the highest power that appears is 1 over x cubed, or is x cubed, so I could multiply both sides by 1 over x cubed. Or top and bottom by 1 over x cubed. So if I distribute on top, we get 1 plus 1 over x cubed. On the bottom, we get 2 over x plus 3 over x cubed. So if I let x get huge, right? That goes to 0. So what is the top approach? What is the bottom approach? So if I take 1 and I divide it by things that are getting closer and closer to 0, what do we get? What? Infinity. So this limit is infinite. Yeah. So I'm going to say something like approaching it, because we still can't divide by 0, but this is what the limit allows us to do. Right? Like, so right up here I can say, okay, the top is approaching 1, the bottom is approaching 0, so the whole thing. Some people adjust this rule and they say instead of the highest power of x that appears ever, divide by the highest power of x that appears just in the bottom. You'll still get the same results either way. It just sort of appears slightly differently. But yeah, so this limit is infinite. The top is growing faster than the bottom, basically, is what that says. Both of these things blow up, right? An x squared blows up, an x cubed blows up. This one blows up faster and outpaces the bottom. Sort of one way we could interpret that. Oh, I just wrote equals 0. Okay, equals infinity. This limit blows up. Let's do another one. And here we're going to be really careful with our algebra. And yeah, we're going to be careful with our algebra. We're going to resist the urge, which I'm sure some of us feel because it's so easy to want to do this. Because everyone would say, like, know what I'm going to say?
Cancel over addition.
Well, we're definitely not going to cancel over addition. Right. What?
Square the bottom.
Like square the bottom, square the top. Let's just get rid of we want to get rid of the radical. We're like, oh, let's just square everything. Can't do that. You can square both sides of an equation, but you can't square the top and bottom of a fraction. Because otherwise you'd be squaring the whole thing. Like, if I could square the top and bottom of a fraction and maintain equality, then 1/2 would be equal to 1/4, and we know that's not true. So, instead, but we have to be a little bit clever about this. We're still going to use that technique where we're going to divide or multiply by 1 over the highest power of x. And it looks at first that that highest power is the squared power. But where does this x squared live?
Under square root.
So what is in effect like the highest power of x? Not to the fourth, just to the first, right? I've got like a squared inside a radical. So like in effect that's really like having just an x to the first. So I'm going to multiply the top and bottom by 1 over x. And then we have some algebra to do. I'm going to take us on a little tangent. Are you ready? Cody, ready or not? We're doing it. I guess I'll go off to the side here. Useful tangent. Back in pre-calc or algebra or whatever it was when you were working with radicals, one of the things we would do is, simplify a radical. So like if I had the square root of 12, I could say, oh, I could factor 12. I got 2 squared times 3. And why was that? Why did I want to factor? Yeah, if I have a perfect square inside, right, that came out as a single factor of 2 outside. And if I have like, 3x squared, like an algebraic expression inside the radical, it works the same way, right? I could take out the x. I have x times rad 3. But this fact that we would use to simplify works in the other direction too. If I have a factor of x outside, I can just throw it in as an x squared. I can have that absorbed into the radical as long as I square it. So that's what I'm going to do up here, like in this limit. I've got 3x squared plus 5 times, and if I square 1 over x, we get 1 over x squared. Now I'm going to distribute in the top and the bottom. In the top, if I distribute that 1 over x squared in the radical, what do we get?
3 plus 5 over x squared.
Mm-hmm. And on the bottom, what do I get?
2 minus 1 over x.
Yeah. I'm going to pause there for a moment and just see what questions there are about kind of either of these steps that we took. Yeah.
How did you do an 1 over x squared on the top and then just a 1 over x on the bottom?
Because I pulled this inside the radical. It's still a 1 over x that I have, but inside the radical it's squared. And so one way you could think of it is,
We're going to be pulling it back out, is what you think? Or not?
no, I don't think we're going to have to pull anything back out.
So you could pull it back out.
What?
X square root of 3 plus 5?
No.
Oh, because it's...
You can't split up a radical over addition.
Okay.
So, Cody, another way to think of this times 1 over x is that I wrote this factor on top as a times the square root of 1 over x squared. Like, these are equal, right? These are the same. You suppose? You know, right?
Yeah, no, that's correct.
So it's like I multiplied the top and bottom by 1 over x. I don't have a factor of 1 over x squared on the top. I have a factor of 1 over x, but when I pull it inside the radical, that's what it looks like. Isn't this great? We're like, I want this to look a certain way, and I can do it. What does 5 over x squared approach?
0.
Yeah, what does 1 over x approach?
0.
So what is my limit equal to?
3 over 2.
Yeah. Now is when I can drop the limit. This is a great example of one where if I could only estimate it numerically. If I was throwing this in my calculator, I would just get decimal approximations along the way, all the way, right? So like, here I can actually find what the limit is. And to estimate them numerically for these types of limits is simple. We're not zeroing in on a single value, just plug in like 1,000, 1,000,000, 10 million or whatever, see what happens. How great is that? This semester is going to be so full of like lots of algebra that we're choosing to do to suit our purposes. Like taking control. It's awesome. What questions are there on this example?